Hello friends, welcome you all on YourPedia education. So friends, as you know that YourPedia is basically conducting a daily 5 question from each and every I can say ब्रांच डिफरेंट टॉपिक्स हम लोग कवर करते हैं डेली, कभी मटेरियल साइंस, कभी कुछ जो भी आपका शेड्यूल है. एंड टुडे आई एम गोइंग टू गिव यू अनदर 5 क्वेश्चंस. कल भी मैंने अपलोड किए थे, उससे पहले टॉम के किए थे. सो टुडे आई एम गोइंग टू डिस्कस 5 क्वेश्चंस फ्रॉम मटेरियल साइंस. आई एम नॉट गिविंग एनी ऑप्शन इन दिस क्वेश्चन, ओके, बिकॉज आई जस्ट वांट दैट यू शुड लर्न द कंसेप्ट फ्रॉम दैट. ओके, ऑप्शंस मैटर नहीं करता है उसके अंदर. सो यू हैव टू लर्न द कंसेप्ट इन ईच एंड एवरी क्वेश्चन. एंड इफ यू वांट मोर क्वेश्चंस फ्रॉम दिस लाइक दिस सीरीज, देन यू कैन visit our website. There you find the more question similar lines के अंदर. Okay, and if you like the questions, please press the like button and जरूर comment कीजिए so that हमें motivation मिलता रहे. questions अच्छे हैं. Now let's start the video. So here you can see the category of questions are difficult type of questions. Okay, and the subject is material science, and this video is useful for gate mechanical as well as XC. Okay, so more oriented toward the XC I can say. Now in this question, given the question as well as solution, so here you can see this is the most important type of question that can be framed from the basics of material science, that copper has an atomic radius of 0.128 nanometer and FCC crystal structure, okay, and an atomic weight of 63.5 gram per mole. Compute its theoretical density. So there are two types of density. First is theoretical density and second is I can say your experimental density. Okay, so you have to just find that. Now for that there is a formula. Directly I can give you formula, that small n into capital A divided by Vc into Na. Now what are these terms? So small n is the number of atoms associated with each unit cell. Okay, associated with each unit cell. So it is nothing but it is effective number of atoms I can say. Okay, effective number of atoms that we use during the calculation of atomic packing factor. Okay, so if I talk about FCC, for FCC there is I can say 6 faces and on each face half atom is present, so total 3 are there and 1 atom at the corner, so total 4 atoms effective that are present. Okay, now A is the atomic weight that is directly given to you. Vc is the volume of unit cell, so volume of unit cell is A cube. And for given I can say crystal structure, there is a relation between A and R. Okay, there is A and R के बीच में relation for body center cubic, face center cubic and for simple cubic. Okay, like for face center cubic it is equal to A equal to 2 under root 2 times R, where R is the radius I can say. Okay, R is the radius of atom. From that you can calculate. Now let's see the Na. Na is nothing but it is a Avogadro number. Directly you can remember its value 6.022 into 10 to the 23 atoms per mole. So directly ये question आया है. अब when you put the values like small n, it is 4 atoms per unit cell. A copper, that is atomic weight given to you. Similarly you can calculate volume is nothing but it is A cube. Here you can see R cube is there, so when you do the cube you can see. Okay, now like this 2 into under root 2 into 2 into under root 2 into 2 under root 2, okay, into R cube. So this is the volume. So 2 into 2 into 2 8 and under root 2 into under root 2 8 2 into under root 2, so it is 16 under root 2 R cube. So this is the volume of unit cell, and R you already know 0.128 nanometer. So you have to convert it into centimeters by multiplying it with the 10 to the minus 2, and Avogadro number is this. Okay, so after calculation you will get the density of the copper 8.89 gram per centimeter cube. So this question is already framed in gate XC, and this is I can say numerical answer type question that is framed. So I hope you like the concept that behind calculation of theoretical density you can see the formula directly that you can use. Okay, and from there you can actually also calculate if density is given and volume is given and Avogadro number you know and atomic weight you know, then from that you can calculate the effective number of atoms. Okay, effective number of atoms, and by knowing the effective number of atom you can say that it is FCC, it is BCC, or it is simple cubic. Okay, from that you can say, like in body center cubic there are 2 effective, and for FCC 4, and for simple cubic it is 1. Similarly you can say. Okay, so I hope ये भी concept आपको अच्छा लगा होगा, यहाँ से ऐसे भी question frame किया जा सकता है. Now next concept is based on Miller indices of plane. So in last video I have given you the Miller indices of direction. Now here you can see the concept behind Miller indices. I have already told to you that first of all you have to see that where this plane is intersecting x-axis, y-axis and z-axis. Okay, so you have to write that in the form of like this. Suppose xa, xb and xc. Okay, like this. Okay, so if any plane is not intersecting any axis, like a plane is parallel to any axis, so they are not going to intersect, so you can put here like infinity. Okay, it is y actually. Okay, so yb and zc, so you can put infinity. After that you have to take the just the coefficients of a, b, c, like x, y and z. Then you have to take the reciprocal of this, and then you have to multiply it or reduce it into shortest form. I will told you the procedure also. Now before analyzing anything you have to see that this plane, make sure yet this plane should not pass through origin. So here you can see this plane is passing through the origin, so you have to shift the origin in this case. Okay, so you have to shift the origin, so you can just shift the origin here like this. Okay, like this. Now if you shift the origin like here is the y-axis, here is the z-axis, here is the x-axis, and this is the origin. Now you can see this is not basically, I can say, passing through the origin. This plane is not passing, but here you can see this plane like this plane is parallel to x-axis, so I can say it is intersecting, not intersecting x-axis at anywhere. Okay, so this is, I can say, infinity a. So when you shift the origin, what is the intersection and what is the diagram looks like this. Okay, so you are just shifting the, here you can see. Okay, now when you see that it is not intersecting anywhere this, so we can say it is infinity a. Okay, and for y-axis I can say that for y-axis, if this is the origin, and this is positive y-axis, so in a negative y-axis it is intersecting at this, and this length is equal to the length of unit cell. So in length of unit cell we will take it as 1. Okay, 1b. And for z-axis, here you can see it is intersecting. If nothing is given, you can assume it as c by 2, that is at the half, so I can say 1 by 2 times c. Okay, now you have to take the coefficients infinity, 1, 1 by 2. Now you have to take the reciprocal, so 0, 1, 2. Okay, so you can see this is already in shortest form, so you can, what you can do, sorry, this is intersecting y-axis at a negative, so you can put negative here. Now you have to put it into the circular bracket, and whatever the negative you have to replace it with the bar. So 0, 1 bar, 2. I can say this is the final answer for this. Okay, so here you can see the final bar for this plane. Okay, so this is the procedure to solve this, I have already told you. Now next question is for BCC iron. Okay, the iron is BCC given. Compute, first of all you have to compute the interplanar spacing. Second is the diffraction angle for the 2 to 0 set of plane. The lattice parameter is this. Okay, the lattice parameter means it is a is given. You have to calculate first of all interplanar spacing, that is DHKL. Okay, so formula for calculating of interplanar spacing, what is the meaning of this? That if this is the one plane of atoms and this is the second plane of atoms, okay, so you have to calculate this, the distance. Now you know that Miller indices of the plane. Remember that if there is a Miller indices of the plane HKL and two planes are parallel, like this is one plane, this is second plane, this is third plane, so Miller indices for this plane is going to be the same. Okay, because the planes are parallel, so they are going to be equivalent, I can say. So Miller, whatever the Miller indices for this plane is equivalent to the Miller indices of this plane, and a is nothing but it is the, I can say, the unit cell edge length. Okay, from that you can calculate distance interplanar spacing DHKL. Okay, so from that a is equal to under root of h square plus k square plus l square. So this is the formula where HKL is given to you. What is that? It is 2, and it is 0, and it is given 0.2866 nanometer. So you can just convert it into the meter, mm, or whatever the units in which they are asking the question. Okay, so directly you can see, here you can see in nanometer. it is 0.1013. okay, so this is the first question. Now next question from there, from the same part I can say, for BCC iron compute the diffraction angle. So now you have to calculate the diffraction angle. For 2 to 0 set of plane, the lattice parameter is this. Also assume that monochromatic radiation having a wavelength of this is used under the order of reflection of 1. What is the meaning of this? That when you just take the planes like this, okay, then there is a technique is called X-ray diffraction. You just strike the X-ray on this atom, and this atom diffract the ray like this. Okay, similarly when you like this, and one ray on this, okay, like this. So from here you can see that this is the angle of diffraction. This is the angle of diffraction, and this is the interplanar spacing DHKL, I can say small h, okay, and I can say this is the, I can say basically you just see here that what kind of interference occurring here. Okay, so detailed concept I have discussed in our course, but here I am just explaining you this is the meaning of this. Okay, now the wavelength of which ray which is striking on this, or the wavelength is just given here, and order of reflection is also given here 1. So let me just give you the relation for calculation of this. So here you can see that sine theta is equal to n lambda to DHKL. So this is the relation that you can remember for your examiner viewpoint, that theta is the angle of diffraction, n is the order of reflection, gamma is the wavelength, and DHKL is the interplanar spacing. So interplanar spacing you already calculated in last numerical, and lambda is given to you, 1 order of reflection is given to you, 2 is in the equation also. So from there it is this, and from theta here it is this. Okay, now I have given you that when ray strike here, so it just diffracted by this angle. Okay, so we given theta is this, but total angle by which wave is just diffracted is this, theta plus theta. So angle of diffraction is not theta, it is 2 theta. Okay, so I think I have just made the mistake जो मैंने आपको पहले बताया, तो just remember that 2 theta is the angle of diffraction that you have to remember. Okay, now the last question of the day and very important question. आपने वैकेंसीज डिफेक्ट्स के बारे में पढ़ा होगा, दैट पॉइंट डिफेक्ट इज देयर, लाइन डिफेक्ट इज देयर, दिस डिफेक्ट इज देयर, दिस डिफेक्ट इज देयर, बट द क्वेश्चन इज दैट हाउ मेनी डिफेक्ट्स आर देयर इफ वी वांट टू कैलकुलेट, लाइक एट दिस मच ऑफ टेम्परेचर व्हेन यू गिव दिस मच ऑफ एनर्जी, देन हाउ मच ऑफ डिफेक्ट्स और हाउ मेनी ऑफ एटम्स आर मिसिंग फ्रॉम देयर लैटिस पैरामीटर्स और लैटिस पॉइंट्स, देन you have to see. Now here you can see, calculate the equilibrium number of vacancies per cubic meter for the copper at 1000 degrees Celsius. That when you take the copper at to 1000 degrees Celsius, then due to the high energy transfer with increase in temperature, the bonds are going to break, and when the bonds are going to break, the atoms are going to left their lattice points, and when atoms are going to left their lattice point, that defect is called vacancy. So first of all, here we are calculating the number of vacancies. The energy for vacancy formation is 0.9 electron volt per atom. Atomic weight and densities are given for copper. This is the atomic weight and densities, I can say, respectively. So here you can see the process. So this is the exact relation for calculation of number of vacancies, equal to n. N is nothing but it is the effective number of atoms. QV is the energy required for energy for vacancy formation. K is the Boltzmann constant, and T is the absolute temperature. There is a negative sign. So energy required is given to you 0.9. Boltzmann constant you have to remember 8.62 into 10 raised to 5 electron volt per Kelvin, and temperature already given to you in degree Celsius, you have to convert it into Kelvin. Okay, so this is very important, just convert it into Kelvin. That is why it is very important parameter. Now this is not given to you number of effective atoms, and it is also not given to you that what kind of, I can say, and basically unit cell is this. Okay, so from there you can directly calculate from this formula that n equal to Na, Avogadro number, into density by atomic weight, that we have already discussed. From here you can see atoms per meter cube we have calculated, and from by putting all the values in this formula, the number of vacancies per meter cube are 2.2 into 10 raised to power 22 vacancies per meter cube. So here you can see that the atoms present per meter cube of volume is 8 into 10 raised to power 28, and out of that total atoms, 2.2 into 10 raised to power 25 atoms are missing. Okay, so here you can see how many defects are there. Okay, so it is very interesting data, I can say. Now Thank you very much, friends. Whatever I have taught in this lecture, I hope you got that, and in each and every question I have tried to cover that 5 concepts I can cover. And this is very important video. Numerical type question generally you will not found on this YouTube channel any. So if you like the video, and basically press the like button, subscribe the channel, and share with your friends, and drop a lovely comment. Okay, happy Teachers Day again. Thank you very much.